This lesson focuses on Le Chatelier's principle. Henri Le Chatelier was a chemist that studied a lot of equilibrium systems and in particular gas systems. So what he did is he took a system at equilibrium and then he adjusted different factors or variables related to the system. And he noticed that if a closed system at equilibrium was subjected to some sort of change, so a change in concentration, a change in temperature, a change in pressure, that processes would occur that would tend to oppose or counteract that change. So what does this mean for us in terms of equilibrium? Well, the term processes usually means that the equilibrium is going to shift either to the left or to the right. So he noticed if he changed the temperature, for example, he noticed a shift in the equilibrium system that it either favored the reactant side or it favored the product side. And that's what we mean by left or right. Okay, left is referring to reactants, right is referring to the products, just simply because of the left or the right side of the arrow. Oppose means that if you do something to the system, it's going to shift in a way to try to undo what you did. So what this means is if you heated up the system, for example, the system's going to shift to either the reactant side or the product side to try to use up that extra heat that you added. If you added an extra concentration of something, it's going to shift in a way to try to use up those extra molecules that you incorporated and do the opposite, bring the concentration down. So one thing we have to remember is that equilibrium only occurs in a closed system. And this is why we can see these changes is as long as there is a lid on the system and we see them reach equilibrium again, we can see the effects of these changes. So let's look at the effect of temperature changes on a system. So let's say we have an endothermic reaction, and we recognize that this would be endothermic in the forward direction because we see heat listed there as a reactant. So let's pretend that we increase the temperature of this system. So again, we always assume it's at equilibrium, it's moving along, reversible rates are equal. And then we're going to come along and we're going to heat up the system or heat up the reaction flask. If we do that, we are going to be adding or increasing heat on the reactant side. So in order to counteract this change, the equilibrium will move in a way to use up that heat. So it wants to react this heat away. And in order to do that, we're going to shift to the product side, because by shifting to the product side, we're going to be making more of our products and less of our energy, less of the reactants as well, but less heat will be around in the system. So we say then that the equilibrium will shift to the right. And again, we often use left and right, just simply the left side of the arrow or the right side of the arrow. Let's pretend, so I'll get rid of all of this. Let's pretend now that we're going to decrease the temperature and we're going to now remove some of the heat out of the system. So right over here, we're going to decrease the heat. So the system realizes that we've lost some heat and it wants to counteract that change. So it wants to make more heat, okay? Try to recoup some of the heat that we've lost. So what will make sense is for these products to say, uh-oh, we've lost some heat, we better make some more. And we're going to shift to the opposite side and we're going to shift to the left to make more reactants. Let's do more of the same now with concentration changes. So here's a equilibrium reaction. And if we add some hydrogen to a flask, so if we increase the concentration right here of hydrogen, the system can tell there's extra hydrogen molecules around in the system that can be reacted away. So to counteract that change, it wants to use up some of the hydrogen. So it's going to shift to the right side. It's going to use up some of those H2 molecules to make a product. Let's say that we can somehow decrease the concentration of iodine. Well, the system can tell now I have less iodine molecules, so let's try to make more. In order to make more, the reverse reaction is going to be favored. And by doing that, the system is going to shift to the left side to make more reactants, which will make more iodine. If we add some HI, so let's pretend we're going to increase the concentration of HI here. Again, the system realizes there's a lot of products now all of a sudden. So similar to the above scenario, it's going to decompose and it is going to shift to the left side to try to decrease that concentration of HI. We missed that blank. If we add more HI, the concentration will immediately increase. So again, they're going to try to decrease that concentration by shifting to the left. So when we talk about gas equilibrium, we can also talk about pressure and volume changes. And we have to recall Boyle's law from our lessons in gas chemistry from last year. So Boyle's law states that pressure and volume are inversely related. So that means if the volume is increased, the pressure will decrease, and vice versa. So if one goes up, the other one goes down. And we have to keep that in mind as we look at these equilibrium systems and change either the pressure or the volume. Now, usually we're changing one or the other. How you think about it or visualize it in your head is up to you. I tend to visualize or think of it in terms of volume changes. And I'll just kind of explain how we do that. So let's look at this ammonia reaction again right here. And we say if we increase the volume of the container, which is also the same as decreasing the pressure. So again, your brain might think better with one variable versus the other. For me, I like volume because what I can do in there, I can visualize space. And I say to myself, okay, we've increased the volume of this container. We had, X number of molecules of reactants and products in there. Now I got more space. So I have all this extra space because I've increased the volume. So what side is my system going to shift to? Well, it's going to cause a shift to the side with more gas molecules. And this makes sense because more gas molecules are going to take up all that extra space in a faster way. Okay, and we want to fill up that space and oppose the increase in volume as quick as possible. So what you have to do is you have to take a look at your reactants and you're going to say to yourself, okay, well, what side has more moles on it? Well, this has 4 moles, right? 1 nitrogen, 3 hydrogens, compared to the ammonia side, which only has 2. So in this case, if I want more gas molecules, I have to shift to the left because I have 4 moles on the reactant side versus 2 on the ammonia side. If I decrease the volume of the container, or again, increasing the pressure, we want to relieve these changes. So if I've decreased the volume of the container, I have less space. So if I have less space, I want to shift to the side with less gas molecules because they're going to take up less space. So in this particular example, and you got to be careful, it's different for every single reaction, which side will create less molecules? Well, it's going to shift to the right side, okay, because the right side has less molecules. 2 other changes that can occur in equilibrium is adding a catalyst. And adding a catalyst, as we know, when we think of a potential energy diagram, favors both sides of the reaction. So if we drew a little catalyst here and we saw that, decrease in activation energy, well, that happens on both sides, the forward and the reverse. So an equilibrium is not shifted in any way by a catalyst. It does not affect anything about an equilibrium system. And then we can talk about inert gases. So remember that inert means gases that don't react with anything. So these would be noble gases. So let's pretend they added a noble gas, argon or helium, something like that, to a system. Well, they're inert. They are not going to react with the substances. And this is important to note because that means it's not going to change the concentration of any of your reactants or your products in the system. But what could happen if they don't allow for the volume of the container to expand, or if the pressure is altered in any way, you may shift depending on, again, whether the volume has grown or not, whether the system feels that there is less space or that the amount of space in there has stayed constant. To know the difference, you have to read the condition very carefully and know what's going on in the actual system. So stop the video and try to answer some of these questions on your own. We're looking at this system right here, and we want to try to get a sense for the different kinds of changes that can occur when we alter the system. So stop the video and then try your luck, and then come back here and we'll give you the answers. So if the concentration of NO2 is increased, here's our NO2 right there on the product side. If I put more of it in, I want to use it up, it's going to shift to the left side. If my concentration of H2O2 is increased, so be careful, there's H2O and H2O2, then that is a reactant. If it is increased, we're going to try to use it up, and we're going to try to make more products as a result. If the partial pressure of N2H4 is increased, so watch the wording here, partial pressure is a different way of saying we've increased the concentration of a gas. Okay, so make sure you note that partial pressure in this case is referring to adding more molecules, right? If you add more gas molecules, you're going to have an increase in pressure because there's more of them colliding in your container. So here's our N2H4. It's a reactant. It's going to shift to the right side to get used up. If the temperature is increased, so here's our heat. If we increase that temperature, we're trying to use it up, and we're going to shift to the opposite side. So we're going to shift to the left. Here we go. Some argon gas is added at constant volume. Okay, so the argon is an inert gas. It's not going to interact with anything in the container. But if you had an equilibrium, so here was your container, and you had all kinds of gas molecules in here, okay? And now all of a sudden we add some argon into the spaces that are there, and it says constant volume. So it means that nothing has happened here with the size of the container. The system itself thinks that it's gotten smaller because those argon molecules are now taking up space in there. So the system thinks that there's less space. And if there's less space, it's going to shift to the side that makes less molecules. And right here, I've got 7 molecules in total, or 7 moles, and there I have 10. It's going to shift to the left. Partial pressure of water is increased. Here's water on the product side. We're going to shift to the left, to the opposite. Temperature is decreased now. If I decrease temperature, we want to try to make up more heat. It's going to shift to the right. The total volume of the container is decreased. Okay, so this is obvious. Total volume is decreased. There's less space now. We're going to shift to the side that makes less molecules. This happens to be the left side for this particular reaction. Total pressure is decreased. Okay, so again, your brain might work better in pressure or volume. Mine works better in volume. If the pressure is decreased, this is an inverse relationship. That means my volume has gotten bigger. I have more space. I need to shift to the side that makes more molecules. I'm going to shift to the right side. And lastly, the concentration of N2H4 is decreased. We're going to try to make up more of it then. We're going to shift to the left side.